On the evening of November 12, 1970, the Bhola cyclone barreled up the Bay of Bengal. There were sustained winds of 240 kilometers per hour and a storm surge, or flooding that raised the sea level, up to 10.4 meters. That's 34 feet. The damaging wind and flooding were devastating, and as of 2021, the Bhola cyclone is the deadliest tropical cyclone in history, killing an estimated 300 to 500,000 people. And the abysmal response of the then West Pakistan government was a factor in the War of Liberation that led to the creation of Bangladesh. Just think about that. A weather system was so powerful, it helped create an entirely new country. Massive weather systems can wreak havoc in an instant like the Bhola cyclone. But they can also move in slowly and create gradual change in our weather for days, like warm springtime rains or a weird unseasonal batch of hail. Understanding when different weather systems occur, how they form, and their impacts is an important part of physical geography. Especially because all weather, from massive thunderstorms to small bouts of fog, drives energy exchange within the atmosphere. I'm Alize Carrere, and this is Crash Course Geography. Weather encapsulates all the atmospheric conditions in a specific place at a specific time. And if you live in the mid-latitudes, or everything roughly between 35 and 55 degrees north and south latitude, you can expect the weather to be predictably unpredictable. A bright sunny day in South Dakota, or the South Island of New Zealand or Scotland can suddenly change to overcast and gray, and then just as abruptly clear up. Day to day, we might not notice what's going on in the atmosphere, unless there's a natural disaster headed our way, or we're stuck doing a lot of small talk. Nice weather we're having today, Brandon. It's so seasonal, don't you think? But there are so many complex global circulation patterns in the atmosphere and the oceans. As we've learned, because the Earth is curved and tilted, the amount of incoming solar radiation, or insolation, isn't the same everywhere. Each year, tropical regions receive 2.5 times more energy than the poles, which has to be evened out with the help of circulation in the atmosphere. The uneven amounts of insolation also cause temperature differences that drive some of the biggest rebalancing efforts. Mid-latitude cyclones, which are also called wave cyclones or extratropical cyclones. These enormous weather systems span 1,000 kilometers or more. Even though they share the word cyclone, a mid-latitude cyclone is a relatively huge circular weather system, unlike the Bhola cyclone, which is a relatively smaller, extremely windy tropical storm. We'll talk more about tropical cyclones later. Mid-latitude cyclones can last a week or more, bringing lots of changes in the day-to-day weather or severe storms as they travel from west to east with the westerly winds. These weather systems can form in the mid-latitudes of both hemispheres. But to zoom into where I live as an example, in the Northern Hemisphere, we see mid-latitude cyclones form along the polar front, which is a band of low pressure in the latitudes just below the poles that sits between two large high-pressure areas, the subtropical high pressure to the south and the polar high to the north. A battle rages in the skies between the warm, moist air from the tropics and the cold air from the poles. In fact, the term polar front was first proposed by Norwegian meteorologists Jakob Bjerknes and Halvor Solberg while studying mid-latitude storms in Norway. The First World War was raging, and it seemed that the boundary between warm and cold air was like a battlefront between the Allied and Central forces. Generally, we can call these two opponents air masses, which are vast bodies of air with similar temperature and humidity that form over a region. Like when an air mass forms over tropical oceans, it will be relatively warmer and more humid than one that forms over the frigid interior of northern Canada, which will be cold and very dry. And as they move, they bring their temperatures and moisture with them. The mid-latitudes get a lot of clashes between air masses. And that's where a lot of the storms and precipitation comes from, because when different air masses come together, they're like water and oil, or Godzilla and Mothra. They don't love mixing. Instead, they meet along sloping boundaries called fronts. For example, if the cold air mass is feeling feisty and moves in on a warm air mass, we get a cold front. The nose of the advancing cold front is like a snowplow, hugging the surface because it's dense and heavy, pushing the warm air out of the way and flinging it upward. And with a cold front comes shifting winds, dropping temperatures, and lowering pressure. If the displaced warm air is unstable and wants to rise and has lots of moisture, we'll get heavy rain from thunderstorms and an advancing wall of cumulus and cumulonimbus clouds. But when a cold air mass backs off, the warm air mass sees its chance and creeps in, forming a warm front. The warm air can't displace the denser, colder air near the ground, so the warm front slides over it like a thick blanket. Overall, a warm front is much less sudden and violent than a cold front and tends to linger, leaving warm, wet air behind. The first sign of one is high cirrus clouds, followed by lower and thicker altostratus clouds, and then still lower and thicker stratus clouds that bring drizzly rain. So different air masses bring different weather in their wake and influence the weather conditions of locations as they pass. Warm and cold fronts are relatively small skirmishes, but wars, or mid-latitude cyclones, can start when cold and warm air meet on the polar front. While these air masses duke it out closer to the surface of the Earth, there's another crusade happening 5 kilometers above them, the upper air westerlies. These winds blow very fast because there's less friction higher up. And within the upper air westerlies, about 10 kilometers above the Earth, there's a wind that blows really, really fast. It's the polar front jet stream, and it travels up to 450 kilometers per hour, wrapping all around the planet. Even though it's way up in the atmosphere, a small change in the path of the jet stream can cause a bend in the polar front that leads to a low pressure area where a warm front moving poleward and a cold front moving towards the equator clash. As the air converging and rising to form a low pressure area turns into a full-blown mid-latitude cyclone, the colder air mass is denser and moves faster, overtaking the spiraling cyclonic warm front and wedging beneath it. And it won't be over until the cyclone is completely cut off from the warm air mass that was its source of energy and moisture. In this battle, both the polar front and the polar front jet stream can also move seasonally. They can steer the cyclonic systems and their air masses across the continent as they follow the sun north into the Arctic in summer and swing down further south in the winter. And no two storms are alike because no two air masses are alike. So with so much going on, you can't blame the weather forecasters too much for not predicting the unpredictable. Now, massive weather systems aren't unique to the mid-latitudes, even if warm and cold fronts do happen there a lot. In tropical and subtropical oceans and seas, we can also get spiraling low-pressure storms, which are some of the largest storms on Earth. A storm that starts in the tropical oceans between the Tropic of Cancer and the Tropic of Capricorn can have incredible winds over 118 kilometers per hour. They go by many names: hurricanes in the Atlantic, typhoons in the Pacific, and cyclones in the Indian Ocean. So we're talking about tropical cyclone storms now, but we're filming this in Florida, near the Atlantic, so I'll call them hurricanes from here on. Unlike the mid-latitude battles between warm and cold air masses, tropical hurricanes form from a single warm air mass. Without a cold air opponent, there's no front. The warm air over the oceans means there's lots of water vapor. So as this warm air rises and condenses, the extra energy released fuels its transformation from a weak low-pressure area into a violent swirling storm, extending up 12 to 14 kilometers and taking up the full height of the troposphere. A chimney effect pulls more and more moisture-laden air into the system. Air is sucked in at the base by low pressure in the eye of the hurricane and sent spiraling because of the Coriolis effect. The air then rises rapidly to the top and is full of water vapor, which condenses and releases latent heat energy, producing thunderstorms and enormous amounts of rain. A great deal of time, effort, and money has been spent studying hurricanes, so we know some things. Like in the Atlantic, the official hurricane season is from the 1st of June through the 30th of November. But hurricanes pop up most frequently in late summer and early fall, when ocean surfaces are warmed to 26 degrees Celsius or more, and the ocean air has maximum humidity. And we've found a correlation between rising sea surface temperatures and longer tropical storm lifetimes and greater intensity in the Atlantic basin. Looking to the future, models suggest that the intensity of extremely severe storms will only increase in the coming decades. But there's still a lot to learn. Like, we can't predict a hurricane's path with great certainty more than 3 days in advance, even though it's tracked by radar, plane, and weather satellites. And where a storm makes landfall becomes the most pressing question as a storm grows and meteorologists track its movement. Hurricanes' source of moisture and energy is the warm ocean air and water, so they grow when they're over water but begin to dissipate once they make landfall. But by then, they could have already caused tons of damage to coastal communities. The boundary between water and land in tropical and subtropical regions is naturally marked by mangroves and wetlands, which absorb the brunt of the storm surge, buffering inland areas from flooding. For example, the low-lying coastal areas of Bangladesh and India form the world's largest delta, and is also the location of the Sundarbans, the world's largest mangroves. However, even with the forbidding ecological buffer, there are also large pockets of people and rural settlements, which ties back to colonial land policies and practices. There's increasing pressure to develop these coastal areas for fish farming, tourism, manufacturing, and oil and gas exploration. All activities that are destroying the mangroves along with the ecological functions they provide. If we combine that destruction of a natural buffer with the scientific fact that the best hurricane warnings are given around 36 hours in advance, we're left hoping our transportation infrastructures can handle a mass evacuation that quickly to save people's lives. And in Bangladesh, the most densely populated country in the world, the stakes for that task couldn't be higher. In countries like the United States, areas susceptible to hurricanes continue to experience population growth, economic development, and urbanization. Even as hurricane warning systems have improved and more lives have been saved, the loss to property and the number of people displaced has steadily risen. Our relationship to weather is complicated because so much of our experience depends on where we build our communities and why. The light drizzle near a warm front might call for rain boots or an umbrella. The thunderstorm near a cold front may have us running indoors and comforting our dogs from the thunderclaps. But the damage of tropical storms can lead to incredibly severe consequences. We can't go anywhere on Earth to completely avoid weather, so our choices about what chunk of the atmosphere to live under matter. Next time, we'll zoom out and look at weather patterns across whole regions when we talk about climate. Many maps and borders represent modern geopolitical divisions that have often been decided without the consultation, permission, or recognition of the land's original inhabitants. Many geographical place names also don't reflect the indigenous or aboriginal people's languages. So we at Crash Course want to acknowledge these people's traditional and ongoing relationship with that land and all the physical and human geographical elements of it. We encourage you to learn more about the history of the place you call home through resources like nativeland.ca and by engaging with your local indigenous and aboriginal nations through the websites and resources they provide.